Hello, this is Group 3's presentation for Lab 3 IC Engine with group members Kevin Agostino, Taylor Chevalier, Irene Cho, and Junyan Lim. The team has been asked to fully analyze a new generator by Generator Systems Inc. based on a modular internal combustion engine. The engine can use either compressed air or propane as fuel and is connected to a 48-volt regenerative motor which can either drive or be driven by the engine. The system also includes an encoder to track the engine and motor shaft positions, as well as a force transducer to monitor the engine and motor torque. The goals of this multi-stage experiment are to characterize the mechanical and fluid properties of the engine, such as dimensions, angle, and position relationships, friction and inertia, and the exchange of energy associated with each component. The final goal is to optimize the engine to generate power that can be stored in the motor's battery. Here's our establishing equation that describes the transfer of kinetic energy into and out of the chosen system, the engine, where I fly is the moment of inertia of the flywheel, omega fly the angular velocity of the flywheel, W air, work of air, W motor, work of motor, W friction is the work of friction, and W piston is the work of piston. A and B denote the beginning and end of the strokes, respectively. All values in red are known variables, while all values in blue are unknown, but can be derived and calculated using clever reconfigurations of the engine that negate certain values. To clarify, here are the ways that changing the engine setup can eliminate variables in the equation. The piston moves in a constant cyclical motion, meaning it does no work and can be removed from all subsequent equations. By removing the engine head and running it at steady state, the work of air and changes in angular velocity can also be eliminated, meaning the work of friction is equal to the work of the motor. Running the engine again from rest eliminates the starting angular velocity. Because the end velocity is a known value, this leaves an equation for I fly. To find the final variable, the work of air, the engine head is reattached to create a 4-stroke cycle. The work of air can then be found using all known variables.
Calibration is necessary so that we may bypass the need of understanding how the amplifier, the Wheatstone bridge, the strain gauge, and the effects of hysteresis link the voltage to the force, or in this case the torque multiplied by distance. This torque voltage curve is assumed linear as a result of the York regression with a gain and an offset voltage. This calibrated torque voltage function, highlighted in red, would then be used to calculate the average torque values using the voltage values from the force transducer voltage per 10-degree bucket. To isolate work due to friction and flywheel moment of inertia, the piston head is removed and the engine is accelerated from rest till a steady state velocity is reached. The necessary components for the calculation of work and inertia are in the following slide. The focus of this slide is how the motor work from arbitrary points A to B is calculated. Because torque fluctuates due to the high sampling rate, the average torque values obtained using the calibration function earlier is numerically integrated to obtain the work of the motor. We'll focus on the acceleration portion to calculate the flywheel inertia, which uses the work of the motor from rest to steady state and the work due to friction from rest to steady state, as well as the steady state angular velocity. Now focusing on the steady state portion, to calculate the work due to friction, the work of the motor from steady state to end is used. This table shows the iFlyer experimental values for both the 4 and single flywheel options. The results match theory where a higher mass equates to a greater moment of inertia. Additionally, the experimental moment of inertia was lower than the theoretical by at least an order of magnitude. This may be because the experimental values reflect the engine as a whole and not just the flywheel.
When the torque done by friction at a given voltage value is calculated, it becomes clear that the magnitude increases with voltage, with an offset between the 4 flywheel and 1 flywheel data. This means that our system is more representative of a Newtonian friction model as opposed to a Coulomb friction model. However, we understand that the results should be somewhere in between. As for why this is the case, removing the engine head negates the effects of both air and the piston, which means that the work done by friction is directly proportional to the velocity of the flywheel. As such, the torque caused by friction must increase if the velocity also increases. The offset between the two sets of data is due to the difference in flywheel inertia. Note that the overall torque appears to be steadying out, which means it's possible that higher velocities would adhere to a Coulomb friction model. However, this cannot be confirmed without gathering data at higher voltage values.
With work friction and iFly calculated, Work error could be found by analyzing 4 cycles of an engine. With the engine head on and the air injection off, the force transducer data and the encoder data was collected at 3 different speeds: low, medium, and high. Using this setup, the system was again tested with 4 flywheels and 1 flywheel. This is an overview of the engine stroke cycle. Theoretically, air should be doing no work on the system during intake, negative work during compression, equivalent positive work during power, and no work during exhaust. The theoretical values of work error were calculated by the equation shown above the figure. This theoretical model makes an adiabatic assumption that the compression happens very quickly and without heat transfer. This equation takes the volume of the piston as well as the volume of the air in the channels into account. The theoretical work error calculated was 0 joules for intake, negative 87.45 joules for compression, the equivalent positive value for power, and the 0 joules for exhaust. Under this model, the net work acting on the engine over a complete stroke cycle is 0. This is consistent with the fact that at steady state, the system is not accelerating or decelerating. Shown in this figure is the experimental torque data from 1 flywheel test at medium speed. In order to find the experimental work error values, a numerical integration was done on the torque versus angular position relationship. This gives the work motor at each engine stroke. However, to analyze each stroke, the data must be segmented. In the first 4 strokes, or in the first 720 degrees of data collection, the lowest torque value always falls at the end of the compression stroke, and each stroke is 180 degrees. Thus, 360 degrees after the lowest torque value was set as the beginning of the engine cycle. Using this knowledge, the data at 180 degrees increments was segmented, and 2 full engine cycles were averaged based on the associated stroke. This is the one-fly data with average cycles at low, medium, and high speed. As you can see, work done by the motor in the compression and power strokes increases in the order of high, low, the median speed. This is because at high speeds, the engine is running fast enough to the point where the motor can do less work to keep the engine running. This is due to the moment of inertia and the higher kinetic energy of the system at high RPM. However, between low speed and medium speed, the work of the motor must increase as the RPM increases. This is due to the fact that the friction has a higher proportional effect in the system at lower speeds. This is our 4-flight data. As you can see, the low-speed data in blue looks like a normal cycle. In comparison, the medium and high-speed data does not have the normal torque trough expected in an engine cycle. Thus, this data was not used for further analysis. This will be addressed later in the presentation. With work friction and I-fly calculated from before, the experimental angular velocity and work motor values, work error can be calculated at each stroke using the overarching equation. Then, using the theoretical work values, work discrepancy can be found. As shown in the table, work discrepancy is relatively low for intake and exhaust. However, for compression and power, the discrepancy is very high, ranging from 76 to negative 90 joules. This is due to the fact that the model has many associated assumptions. The model assumes that no energy is lost through heat transfer and that the system is airtight. Thus, it's assuming that the entire volume of air in the piston is directly contributing to the engine. However, the flow losses are not negligible, and air escapes the system, especially during the compression stroke. This explains the high work discrepancy in the system.
These are the combined uncertainties of the motor, the encoder angular displacement, and the calibrated torque measurement for all 3 low, medium, and high speeds of both 1 and 4-fly configurations. If the work discrepancy is less than the combined uncertainty of the motor, we may conclude that the overarching equation may be an accurate model for the 4-stroke IC engine within the experimental uncertainty margin. However, since work discrepancy for the compression and power stroke are about in order to 2 magnitudes larger, we may conclude that thus far the IC engine may not be modeled with the overarching equation within experimental uncertainty margin.
The 4 flywheel data collected to derive the work done by air is not ideal, and so part of our remaining time will be spent regathering this data to see if what we have is valid. This also means that the effects of removing the flywheel cannot be analyzed as we cannot accurately compare the 2 datasets. As for air injection, The ideal injection timing was determined to be between 40 to 90 degrees after ignition, and the next step is to measure the performance difference the injection has on the system.